So thanks a lot for this opportunity to give a talk. And let me first tell you some comments about the title of my talk, just to give you a flavor of what I'm going to talk about. So I'm going from the end to the beginning. So the talk will be about QCD scattering amplitude. And there is no reason to convince you that the subject is so important. We have to have some information about QCD scattering amplitude for various reasons, including LHC physics. And the reason why we are here, we want to learn something about QCD scattering amplitude by going to another theory, which is maximally supersymmetric n equal 4 Young-Mills theory. And everybody loves this theory because it has a lot of nice features, a lot of symmetries, and we believe that it's just a question of time that the theory will be solved, certain approximation. So then the object which I'm going to describe will be scattering amplitude, and at that moment let me just quote the last paper by Lance Dixon saying this is the most perfect microscopical structure in the universe. And finally, dualities. Dualities normally, in the way how you will see dualities appear, it will be sort of an interconnection between different quantities. And normally when we talk about duality interconnection, we're looking for some symmetries. So the main idea of my talk will be just to show you that there is some hidden structures behind scattering amplitude both n equal 4 in QCD. And what I will try to do, I would start with n equal 4 when we have more or less complete understanding of those structures. And then by the end of my talk, I will show you that some remnants of the structure will survive when we go to QCD. So if you're not interested in n equal 4, you could sleep for first 15 minutes. And if you're interested in QCD, just wake up for the last 10 minutes. So let me first define what kind of object we're going to study.
Stay awake for the middle half hour?
So I'm going to discuss basically three main objects. So first object is just scattering amplitude, and by scattering amplitude we mean scattering of asymptotic states. And just to simplify the consideration, I have chosen the most simplest amplitude you could imagine, just amplitude of scattering 4 gluons. So you have 4 gluons, each of these gluons has two-dimensional momenta and some helicity, and then what we'd like to do, we'd like to study this object, both n equal 4 in QCD, and just to get information as much as possible about the dependence of this object as a function of the coupling constant. So the second object which will appear in my discussion will be Wilson loops. So as you know, Wilson loops is just defined as an expectation value of circulation of the gauge field along certain contour. Let's call it C. And by the definition, this object just lives in Minkowski spacetime. So you specify the contour and you can compute this object in Minkowski spacetime. So as you see, it becomes some function of the gauge field, and since you have integration of the gauge field along the contours, this object, strictly speaking, is non-local. You could always decompose this infinite sum with the correlation with the gauge fields, but in the first approximation, you could think like non-local function of the integration contour in Minkowski spacetime. And the last quantity which will appear in my discussion will be correlation function. So let's take some operators. So again, it doesn't matter whether we n equal 4 in QCD. You could always choose some so-called protected operators. In the case of QCD, it could be, for example, electromagnetic current, but in n equal 4, you know, supersymmetry enhances symmetry, so you have plenty of those operators. But don't specify for the moment this operator, just let's say such operator exists. And then what I would like to do, I would like to study correlation function of, say, 4 operator. It will be the first time when the structure with the form of this correlation function is not fixed in Rickley-Becker form of symmetry. It's just function of coordinate Minkowski spacetime. And again, all these three coordinates could be well discussed both n equal 4 and QCD. So now let's think, is it possible, do this object relate in a certain way? So as I told you, a Wilson loop is a local object defined in Minkowski space. This object is local function of, in this case, 4 coordinates, whereas this object amplitude by definition, by the construction, is naturally lives in momentum space. So somehow this object and this object, they live in different spaces which are related to each other by some sense by Fourier transform. As a consequence, you don't expect to find any relation between them. But imagine such relation exists. So imagine, and this is basically the idea of my talk, to show you that such a relation exists. So imagine you have some kind of relation between these three objects. So if the relation between these objects exists, it would mean that if you know everything, for example, about the symmetry of one of these objects, you automatically will know something about another object. So let's think about the relation between these two objects. So if amplitude in some way related to the scattering amplitude, it would mean that all symmetries of the scattering of the correlation function automatically will have manifestation at the level of the amplitude in vice versa. So what's those symmetries? So the symmetry to a conformal symmetry, right? So if your symmetry is conformal, which is the case in equal force Biot-Mills theory, but not the case for QCD. But nevertheless, if the symmetry is conformal, you know how conformal symmetry acts on the correlation function, and if you know conformal symmetry is a transformation which acts locally in configuration space. So something which acts locally in the configuration space definitely will have no localization of the level of the amplitude. So therefore, conformal symmetry, the same conformal symmetry realized at the level of the correlation function of the amplitude will have different form. But now, if you're saying that amplitude, roughly speaking, proportional to the correlation function, it would mean the same conformal symmetry, which was native for point of the correlation function, becomes dual for the amplitude. So in this way, having the relation between amplitude and the correlation function, you have to conclude that amplitude enjoyed two symmetry. One of them was native conformal symmetry of the theory where amplitude was defined, plus additional dual conformal symmetry induced by this relation. And if you're thinking about the simplest example when such a relation is realized, it's just harmonic oscillator. So think about harmonic oscillator as a ground state wave function. So if you take harmonic ground state wave function, which is Gaussian function, you take it Fourier, and you will get the same function. So somehow this duality relation tells that you could start the same function, define different representation, and by some reason this function coincides if you go from one space to another one. Well, the reason why it coincides, we know, because harmonic oscillator is exactly solvable model. So therefore, every time you have such kind of the relation between two functions define different representation, it should be a signal about the existence of additional symmetries, eventually integrability. So the idea of my talk will be to convince you that actually these three different quantities are interrelated to each other in certain limits. So what are those limits? First, let me start from the first, the horizontal line. So you have scattering amplitude, and here you have Wilson loop. As you know, and you have heard from talks at the beginning of the program, indeed we know that there is a relation between amplitude in certain bosonic Wilson loops. And this relation goes as the following way. So you start from the amplitude. Amplitude is defined by the configuration of all light-like momenta, which sums up to 0, and some moment, each momenta is light-like. And then out of this four momenta, you construct contour, which is rectangular contour with edges being momenta. And then, if you formally identify this contour to be embedded in Minkowski space-time, then the claim is that these two objects actually dual to each other. Dual in the sense that perturbative correction to the amplitudes turned out to be identical to the perturbative correction to the Wilson loop, modular terms which vanish if you go to multicolor limit, and if you neglect terms proportional to the parameter regularization. So now what about, so this duality sort of has been checked, and we have a little doubt that it's there. So what about another two dualities? So this duality between Wilson loop and the correlation function I will review shortly, just based on the paper which I wrote in collaboration with Fernando Alday, Burkhard Eden, Juan Maldacena, and Emery Sakachev. And the relation between amplitude and the correlation functions is a work which is done in collaboration, again, Burkhard Eden, Paul Heslop, and Emery Sakachev. So I will go on to talk about this relation, as I told you, in the simplest case when you have foreglown amplitude. In this case, basically, this picture will have to do with so-called Amici amplitudes. That is the reason why he will be dealing with bosonic Wilson loop. As a consequence, as well as the correlation function, we will be dealing also with simplest class of the bosonic correlation function. I believe that Emery is going to talk later in the program about generalization of this picture to most general case of all superamplitude. In this case, amplitude becomes super amplitude and equal for theory. This becomes super Wilson loop. And I believe we already heard talk from Dave and from Simon about the same object. And finally, this correlation function will be generalized to be super correlation function. But again, as I told you, I'm going to simplify these things and explain this relation in the simplest case of four-particle, foreglown Amici amplitude. Any question? Okay. So let's start discussing object one after another. So let me start from the amplitude. So again, as I told you, at the very beginning I will be concentrating mainly in n=4 theory, and then later I will go to QCD. So let's start from the amplitude, and let's start from the three-level contribution. So the level of threes, you just have 4 diagrams, which you have to sum up. So each of these diagram involves self-iteration of the gluons, and you could immediately see, since you have here only one particular type of the vertices, the same amplitude takes the same form in any gauge series. So this, as a level of the tree, this amplitude will have the same form both n=4 and QCD. And also, as you know, that if you start playing with different polarizations, the only level of the tree which is different from 0, it will be the one of MHV type, which means 2 gluons helicity plus, 2 gluons helicity minus. So the first comment is that if you're computing this amplitude, here you have a vertex which comes with a coupling constant G. So in n=4 series, this becomes one of the parameters of the series, just coupling constant, which just depends on any other scales. Once you will go from n=4 to QCD, and in general any gauge series where conformal symmetry is broken, this coupling constant will be actually running coupling constant, normalized at a certain scale. And then since the amplitude should be at the end of the day observable, which means depending on this parameter, you're expecting the level of the loop corrections, depending on the scale, will be fixed in a certain way. But n=4, you don't care about this. But nevertheless, you have to keep in mind that you're expecting already at this level that the level of the loop will be different between two theories. So then you go to one loop level, and one loop level you find that the loop correction to this amplitude are defined by the following integral. Okay, let me first draw the diagram. Just one loop scalar box. Before. And again, what you do, I believe somebody already mentioned this, you go to dual coordinates or rigid momenta coordinates, and you associate with the same diagram, dual diagram. So instead of having loop momenta integrate over, you just introduced a dual coordinates for the loop momenta, and then this becomes integral, which goes over this center coordinate, connecting with the external point by propagator, right? And as you know, this was the starting point for discussing this dual conformal symmetry. In other words, if you just look for this expression, if you forget for the moment that here integration goes to d dimension and d here will stay for 4 minus epsilon, we introduce dimensional regularization to deal with the first singularities. So once you forget that here you have d and not, if you simply put it here, for here, you will immediately realize that this integral actually will be invariant and the conformal transformation acting on this axis as if they were a coordinate. So this was the first manifestation of dual conformal symmetry. Again, it's dual because it acts on axes which are intrinsically momenta in the same way as if they were a coordinate. And as I remember from discussion we had at the very beginning, this is a signal there is some dual symmetry should be appear, and basically this was the beginning of a long investigation which led to the formulation of dual conformal symmetry of the amplitude. So here you have this integral, and then you could compute this integral. Then what you will find certain expression which will develop poles in epsilon together with finite part, and then there was further development which goes under the name of A, B, D, K, BDS on that, which led to the formulation of the following conjecture, which tells you that if you take a ratio of all loop amplitudes in this particular case, divide by the tree and take the logarithms, then this expression will have a remarkably simple form. So there will be some divergent pits which will involve poles in the epsilon, plus some finite contribution. And then I will use this finite contribution later in my talk, so let me write it explicitly. So what do we have here? So we have here logarithms, which means that at the end of the day amplitude, everything is here exponentiates. So on the right hand side you have sum of two terms. So I expanded the resultant powers of the prime dimensional regularization and throw away the terms which are explicitly proportional to the prime dimensional regularization to epsilon. So here you have divergent pieces which are given by the sum of the poles, and here you have finite pieces. So the finite pieces involve two functions which are functions of the coupling constant. So one of them is called Caspar anomalous dimension, another called so-called collinear anomalous dimension. So the Caspar anomalous dimension appears in front of the expression which depends on this time invariant S and T, and here you have second power of the logarithms. Mu square is prime dimensional regularization. So second power has to do with the fact that this integral actually develops double pole, and then if you expand double pole expression, you have log square over parameter fat regularization. And finally, here you have pieces which log square of the ratio of the time invariance, which doesn't depend on the parameter fat regularization. So second line, again, it has so-called collinear anomalous dimension, and the corresponding function in front has simple powers of logarithms. So this function, it's a function of the coupling constant which has infinite series expansion starting from one loop, and this function, it has zero contribution at one loop, but starting from two loops, it has expansion which goes to two loops. Right? Yes, this expression is planar. Yes. At the level of one loop, there is that expression. At the level of one loop, you don't see no planar correction. The planar correction to this amplitude will appear starting from two loops. So therefore, strictly speaking, you're right that you have to put here 1 over n c square. But later when we're talking about one loop contribution, at the level of one loop, this is the exact statement. So now let's now go to the second object, which is Wilson loop. And again, I told you that what you do, defining this object, you just choose this particular contour. Again, with the contour edges being dual momenta. And then what you do, you're calculating expectation value of the Wilson loop along this contour. And technically what you're doing, if you just expand the Wilson loop, let's call it VC4, 4 refers to the number of edges, what you will find is that at one loop level, it will be just given by the double integral of a contour. And what you're integrating, just integrating of a gluon propagator attached by both ends to various segments of the contour. So diagrammatically it goes as follows. So if I depict by double line the contour, so these are my integration contour. Let be P1, P2, P3, and P4. Then what you're doing computing the Wilson loop, you're just looking for all possible configurations. So what are those configurations? You may have gluon exchange like this. You may have gluon exchange like that, or you may have contribution like this. So at one loop level, we basically see different types of contribution. You sum them together, and then first things which you will realize that there will be very specific ultraviolet divergences due to the fact that here you have a cusp. So again, you introduce dimensional regularization with 4 minus epsilon to regularize those divergences. Then you sum those contributions. Each of the contributions separately is gauge dependent, but some is gauge independent. You sum them together, and at the end of the day, what you obtain an expression which looks almost like this, with only difference that S in these notations, it will be P1 plus P2 square, with just the distance between these 2 points. Let me call it x1, x2, x3, x4. So this will be distance between points on the Wilson loop, which correspond to one of the diagonal, and T will correspond to second diagonal. So once you will finish the calculation of this object, just one calculation, you will find expression which has exactly the same form with one loop expression for the Caspar anomalous dimension, and as I told you, this time will be absent at the level of one loop. So at this level, you empirically find that one loop correction to the Wilson loop matches one loop correction to the scattering amplitude. Right? So now let's ask ourselves the question, what will happen with these two calculations? Again, let's remind one again. So the relation between two quantities, this one and that one, has been verified up to two-loop level for various configurations, and you have heard a few talks about reminder functions. I'm not going to go into details, but simply let's just ask the question, what could happen with this relation, with duality between these two objects if you go from n equals 4 to QCD? So first of all, we start with amplitude, and I told you that once you go from n equals 4 to QCD, you have to find at the level 1 loop certain terms which will fix dependence on the coupling constant, the scale. Basically, you have to find some integral which will be divergent, so that after regularization, they will introduce a dependence on the right cutoff, and finally they will fix dependence on mu. Definitely not this integral, which is finite, which will do it. So what you have to do, you have at the level of QCD, what you have to do, you have to add additional contribution. And actually, it's very well known that at the level of QCD, what you have to do, you have to add additional so-called bubble and triangle contributions. So those contributions will do two jobs. First of all, they will indeed introduce some contribution proportional to beta function, which is needed to fix value of the coupling constant. And second thing, they will break dual conformal invariance. It's known that triangle and bubble contributions are not consistent with dual conformal symmetry. Another way, going to QCD, you will rule out completely this symmetry. Now you go to Wilson loop and you ask yourself the question how QCD correction will modify this Wilson loop. And you could see that calculating one loop Wilson loop, the only thing which we use is just use glue and propagator. So it doesn't matter which theory you're talking about, this expression for the Wilson loop will look exactly the same in any gauge theory. The difference between different series will appear only starting from two loops. In the first diagram, which will give different contribution in different gauge theory, it will be the one when you have gluon dressed by self-energy corrections, and by this blob I mean all loops with all particles propagating inside. So this will be the first time when we will find gauge theory dependent contribution to the Wilson loop, and as I told you, by definition it will appear two loops. So therefore, given the fact that you have at the level of the amplitude QCD contribution appearing in one loop, at the level of the Wilson loop, a two loop, immediately see there is no way how you could match one loop QCD contribution against one loop Wilson loop. Another way, at the level of already one loop, you see explicit breaking of the duality between Wilson loop and the amplitude. Right? Nevertheless, we will see later in my talk that actually there is a limit in which this duality will be restored. So let's now go finally to the last quantity which I want to introduce, and this last quantity will be correlation function. So again, we're staying in n equal 4 theory, and now I want to consider this correlation function for very special choice of the operator. So I told you that in n equal 4 you have plenty of possibilities to choose those operators. Let me choose the simplest one. So you know that in n equal 4 theory you have 6 real scalars, and let me take two of those scalars, make it complex. Let's take scalars complex Z, and then let's look for the operator, for example, which are bilinear in those complex fields. And now let me introduce conjugate operator with just trace of Z bar square operators. So these operators are protected, which means that they don't receive corresponding conformal weights, don't receive corrections.
When discussing Wilson loop,
Yes.
is there a difference between symmetric Wilson loop and non-symmetric?
Depends what they call the supersymmetric Wilson loop. What you heard from Simona, did you talk about supersymmetric Wilson loop?
But I'm referring to gyroscope.
What's special about this Wilson loop that each of the segments is light-like. So if you start with a Gaussian supersymmetric Wilson loop, which has both integration contour on Minkowski space on S5 and S5, then supersymmetric condition would be that you have to have tangent vector on S5 equal modulus tangent vector on ZDS5. And since we're dealing with light-like contour, it automatically means the scalar contribution is absent there. So therefore, the level, if you're staying within the space, this class of the Maldacena Wilson loops, this is exactly the same Wilson loop which will appear in both theories. Any further question?
Another question. Is there something special about ST equal 1, S, when collinear term vanishes?
ST equal 1.
S times T equal 1. S.
You cannot say S times T equal 1. It should be dimensionless.
Okay.
S divided by T. S equal to T. as we will see later, just to anticipate what will happen, the special limit where something will happen, it will be the limit when s is much bigger than t. As soon as s and t are the same order, you don't see nothing new, nothing nice, let's say, coming from QCD calculation. But nice things will come if you go to the special limit, which will be s much bigger than t. But it will be just my talk. So now let's go to correlation functions. So again, I define the operator. Now I would like to study the property of this correlation function. So let's look for the correlation function, which involves four of those operators. And let me put these operators at 4 different points. And start doing the calculation. So at the tree level, what you will have, you will just have product of 3 propagators. So here I have this arrow line just to denote the propagator of z and z bar fields. So you compute this object as usual.
You don't consider the disconnected diagram?
I don't consider disconnected diagram. There is indeed a disconnected diagram which will look like this. So this disconnected diagram will give the contribution which will be proportional to nc fourths, one of the x1, 2, 4, x3, 4, 4. But now I want to consider the contribution for the nc square, and this connected contribution will come with the product of the corresponding propagators. So this is, again, 3-level expression. So what could we say about the property of this correlation function if we include dependence of the coupling constant? So we know that this object correlation function for operator should respect conformal symmetry, and conformal symmetry dictates you that all loop correction which could dp and this quantity if you include dependence of the coupling constant, it will induce dependence on the conformal ratios. And in this case we're dealing with, you have 4 points, and you have 2 conformal ratios. It's 1 conformal ratio, let's call it U, and the second conformal ratio, let's call it V. Right? And then there was a lot of activity in late 90s when people worked out variable arithmetic technique for computing this quantity, this function, to 1, 2, 3, 4 while loop level. So let's examine the expression for this function at lowest order. At lowest order, which means first power of the coupling constant. So the expression goes as follows. So one loop correction to this function is proportional to the following integral. So just the result of the explicit calculation. So you compute one loop correction to this guy, basically will come from the exchange of the gluon with various possibilities, so you could touch various way. You do the calculation, and here becomes the result of one loop calculation correction to this function of harmonic ratio. First of all, what you verify that indeed this function is conformal invariant. So if you perform conformal transformation of all points entering this integral, you find this invariant, therefore it should be function of u and v. And second, what you do, you just compare this integral here with the one which appears here. So let's compare them. So first, what you note is that there is mismatch factor 2, right? So there is factor 2 in the denominator and there is no factor 2. But it's a sort of slight detail, but it's important in what follows. The second difference, here you have d-dimensional integration, here you have 4-dimensional integration. So what's the reason for this? The reason for this is that when calculating this correlation function, we have this x1, x2, x3, x4. There's a point in Minkowski space-time which defines position of the operator, and defining this correlation function, you're explicitly assuming that all of these points are separated. They're not sitting on top of each other. In particular, this implies that x1, 2 square is different from 0. But now if you go back to this integral, and you ask yourself, what was x1, 2 here? It was just exactly stellar momenta. And since we are dealing with amplitude, this P1 momenta from the very beginning was light-like. So the difference between amplitude and the correlation function, that when you examine these 2 integrals, and the correlation function is treating the kinematics when distances are not like, whereas for amplitude, when you from the very beginning a situation when they are like separated. As a consequence, once you have the distance different from 0, this integral is well defined for dimensions. So you don't need to introduce any regularization if you compute it explicitly. And if you compute it explicitly, what you will find this. So you'll find some expression. I have to be careful here. What you will find certain expression, but now what I would like to do, I would like to sort of simulate a limit which you have the level of the correlation function as the level of the amplitude. Namely, I want to go to the limit when x12 square goes to 0. When I mean it goes to 0, it basically means that x12 square becomes much smaller than any other parameter which I have here. And let's say I want to go to the limit when this x12 square is smaller than everything else. And similarly, I want to go now to the limit when x, let's say, 2c square goes to 0 simultaneously. So if you now look for the definition of this conformal ratio, it means basically that what I'm doing, I'm going to the limit when u and v become simultaneously small. Right? And these limits somehow you're expecting to will be, mimic the kinematic configuration you have here. So if you do the calculation in this case, you will find this formula I've written before. So you'll find the expression which has coupling constant times log of one other parameter u times log of another parameter v. So you have double logarithmic contribution which is perfectly finite, but which depends on these two conformal ratios. So now you compare this with this expression. So this expression from the very beginning was divergent, right? I had to introduce dimensional regularization, and as a consequence I have mu square. But now if you look for the structure of this term and this term, you will see there is a lot of similarities, right? So you have log square here, log square here. Now this suggests you that there should be some relation between these two. So how could we describe this relation? So let's examine two different scenarios. Now, scenario number one. So what we could do, once we arrive to this integral, we could say, let's now return back to our expression for this correlation function. Let me examine the ratio of the correlation function over its three-level expression. So if you just take this ratio, what will happen if I take this ratio? Basically, I will kill this prefactor, right? Because this prefactor is just given by the product of three propagators, and I told you it will be universal prefactor which will fit as all level expressions. So once I have this ratio, I could take this ratio, it will give me this integral, and once I have this integral, now I could take a limit of this integral when all two adjacent point goes to 0. So this integral, it will be defined only in 4 minus 2 epsilon dimensions. And now if you compute the corresponding expression, you will find exactly this integral. Modulo factor 2. So in this way what you will find is the ratio of one loop correlation function over H3 in this particular limit will be exactly equal twice the ratio of one loop MH amplitude over 3. And this factor 2, again, it originates from the fact that here you have p square and here you have twice p square. Okay. So what this relation tells you is that if you consider the ratio of correlation function over H3 at least at one loop level, take the ratio, go to light-like limit, then introducing dimensional regularization, you at one loop level explicitly reproduced twice the ratio of the amplitude.
Even though you're not going to show us this, the claim is that this will generalize to higher loops and to...
Yes, I'll come to this. I will give you the argument why I do this so. But at this level, the way how sort of you discover this too is just by examining corresponding integrals. I won't give you any reason so far, but you will see the reason will appear. So the second way how you could sort of find the link between these two, you could say, let me think about integrands. So here you have certain integrand which you integrate over. As soon as you're looking for the integrand behaves nicely in the conformal transformations, even though you integrate it with the dimensions. This function which stands here has nice conformal properties on the dual conformal transformations. Will be covariant, not invariant, but covariant. And then what we could do, we just compare integrand which appears as the level of the amplitude with the integrand which appears as the level of the correlation function. Both are rational functions of momenta, and you could see, again, the same relation will hold. So integrand of ratio of correlation function will be identical to the integrand of ratio of the amplitude. Twice. And then, as David already spotted, if you go to high loop level, so what will happen is that this relation will generalize the following way. So now, going from one loop to two loops, so what we will do, you will say that if you take all loop expression for 4-point correlation function divided by the tree, take this light limit, the claim is that this object will be equal twice, it will be given by the amplitude, all loop level amplitude, divided by its tree-level expression, power square. So this square, if you expand to one loop level, will exactly reproduce it too. But the statement is that this relation should hold to all loop level. And similarly, the level of the integrand of the ratio of correlation function will be proportional to the integrand of amplitude square. So this was about amplitude. Now let's try to do sort of similar exercise, trying to see whether computing this object you could reproduce something which looks like Wilson loop. So how to do this? Let's look for this diagram. This diagram. Let's do the following thing. Let's just examine one gluon exchange. Here you have.
Sorry, can I ask them? A priori, at higher loops, those two relations, at one loop they were more or less the same.
Yes.
But at higher loops they are very different, right?
They're definitely very different, starting from two loop level. For example, if you expand this relation, let's take first relation. So if you're writing G4 over G0, like 1 plus something for the 1, let's call it I1, plus for the A square, A2. Let's put here index G just indicates the refer to G. And similarly for the amplitude, what you will find at two loop level, you will find that E to G will be equal twice E to A plus E1A square.
This is from integrand, yeah?
For both relations. I mean, it doesn't matter whether you go to integrand to the amplitude, there will be the relation which will follow from the fact that here you have square. So you expect it to have such term proportional to one loop integrand squared. And indeed, you could verify it explicitly. Since you know the loop expression for this object, for this function, you could repeat the same analysis and to compare the corresponding limit of this function with the corresponding integrand and the amplitude computed from this side. And you see that exactly the same relation appears.
When you're squaring the integrand, you think squaring also the propagators. Right?
No. What I mean that if you square, so here when you're talking about integrands,
Yeah.
so this amplitude that you have here, this ratio, it corresponds just to this cross diagram. So this one loop ratio integrand.
What I'm saying,
Yes.
in a square where you have it squared,
Yes.
right? So that's divided by the tree.
It's divided by 3. It's always divided by 3.
Right. So that means that are you squaring also the propagators in the? You have to.
It's this object here. Let's do it. So what is the integrand for? Yeah. Mm-hmm. So let's start from amplitude. So if the level of amplitude, what you have here at one loop level is just this color box. And the corresponding integrand is just the cross. If you go to dual variables and the cross, external points, it will be just exactly those coordinates. X0 integration point, dual to loop momentum. Now you go to two loops. And two loops, what you will find here, it will be two diagrams. Right? Then you go to dual picture. What you will find this and cross diagram. Right? Let's follow notation x1, x2, x3, x4. Let's think about this diagram. It has 2 points, so therefore let's call it x0, x0 prime. We have 2 integration points corresponding to loop momenta. So now I take this function, which is a rational function depending on 4 external coordinates and 2 internal one, and I add 1/2 square of that function. And when I square it, what I do, I'm multiplying this cross diagram by another cross diagram when external points are exactly the same, but internal points x0 prime. So in this way, what you do, you just take in this function, which is a reducible function in the sense that it cannot be written as a product of two functions depending on these 2 points. And you add product of functions which have the same external point but different internal point with additional relative factor 1, 2. So the claim is if you sum up these 2 functions, what you'll obtain, it will be integrand corresponding to 4-point correlation function.
Yes, but then the answer to my question is that indeed with x, if you put different variables, it's clear that the 2 relations are more or less the same. The one where you square the result and the one where you square the integrand.
No, it's not the same. They're not the same because...
they are similar. More or less they are the same.
No, as usual, everything is hidden in details. What's hidden in details is that if you're computing the integral, so the integrand itself is not a well-defined function if you start doing integration of the corresponding internal points. You have to do some regularization. So what this relation tells you, that if you introduce regularization, the same, let's say you start from equal for theory when you regularize certain way. Then if you calculate in the same theory these 2 quantities, first integrating of the phase spaces, then comparing the corresponding quantities, they will match. And this is a wiki statement saying that even before the integration, if you just look for these 2 integrands and just put epsilon to 0, just remove regularization, you will find there is matches level of the integrands. But going in this way, it's just a question how you deal with this regularization. Regularization could spoil this relation. So I have 15 minutes left, so I promised you to go to QCD. So now let's finally... Say again?
We started late.
Ah,
We have more time.
very good, very good. If just one last comment about correlation function before I switch to QCD. The comment is the following. Now let's try to ask the question, could we predict sort of from the first principle the structure of the integrands? So is there any way how you could predict this integrand without actually doing elaborate calculation? And to see this, let's again start from the same correlation function. And what we like to do, we like to understand the structure of perturbative correction to this quantity. So to do that, let's apply operator, which is g squared d over d squared. So what to do, I apply this particular differential operator to the correlation function. So g squared is just coupling constant. So if you write the integral as a path integral with some particular measure corresponding to n equal 4 Young-Mills reaction, this derivative inside the path integral will act on the measure, right? And at the end of the day, what we will obtain is that this object will be proportional to the integral of the corresponding point with derivative of the Lagrangian with respect to coupling constant, and the same operator P inserted inside the correlation function. Right? I just apply derivative to my path integral, which defines this correlation function. So now, so this relation is just exact consequence of the exact definition of the correlation function. Now imagine I want to compute the first line at 1 loop level. So at 1 loop level, what will happen if I want to know this object at 1 loop level, it's sufficient I compute this guy at the level of the trees. So there is kind of the iteration to compute this at 1 loop level, I have to do it at the level of the trees. But now if you go back and you ask yourself how the structure of this guy looks like, so remember at the level of g squared you're expecting to find this function f, some integrand. So what the relation tells you, actually what we call integrand is just exactly this function. Another way, integrand of the ratio of the correlation function over its tree at 1 loop level. It just proportional to the correlation function of the same protected operators with the new protected operators, just derivative of the Lagrangian with respect to coupling constant, calculated at the level of the tree. So the power of this relation is to know 1 loop integrand. It's sufficient to compute this quantity at the level of the trees. Then you could continue. So you could go from 1 loop to 2 loop to n loop. And finally what you will find, following this logic, that if you want to know integrand of the ratio of correlation function to its trees, what amounts to, it amounts to inserting here, inside the correlation function, n copies of the derivative of the Lagrangian with respect to coupling constant computed always at the level of the trees. So this way, what this relation tells you, it's related to integrand at the loop level to the correlation of primary operators at the level of the trees. So this correlation function, by definition, it respects conformal symmetry of your theory. And therefore, the integrand which stands here, by definition, also respects the same symmetry. And since later we map this integrand into integrand of the amplitudes, this relation automatically will tell you that the corresponding integrand for the amplitudes will also have this conformal symmetry of the correlators, which from point of view of the amplitude is just dual conformal symmetry. Another way, integrand for the amplitude will respect dual conformal symmetry in virtue of this relation. And this relation gives you sort of a very powerful technique how using various tricks coming from conformal field theory could compute this quantity for arbitrary number of insertion. And Emery will tell you later in the program how you could use the same relation to reconstruct correction to corresponding integrand, including dependence of the Grassmann variable, which corresponds to going from MHV amplitude to whole superamplitude in equal for theory.
Is there any hope for some kind of similar statement at non-planar level?
The problem with non-planar limit, as far as you think is the level of the correlation function, you see, arriving at this relation, I never use planar limit. So this relation is exact. It doesn't matter whether you're on planar limit or not. The problem with planar limit appears once you start matching this quantity in the corresponding integrand for the amplitude. And since we know that already at the level of two loops for this particular object, you have explicit breaking by dual conformal symmetry for non-planar corrections, it's very unlikely that relation between correlation function and amplitude will persist. So now, I promised you at the end of my talk I will go to QCD. So far we were staying in unequal force theory. And as I told you, unequal force theory is so beautiful that all these three quantities are related to each other. So now what happens if you go to QCD? So when you go to QCD, again, here we'll be dealing with foregoing amplitude in QCD. Here we will be dealing with the Wilson loop in QCD. And this will be Wilson loop exactly of the same configuration. And here we will be dealing with the correlation function for operators, which let take be electromagnetic current, so protected operator which don't receive correction to the conformal weight. So now the statement is the following. So if I go to this particular limit, namely I took it for correlation function and I take in two neighboring points to be like separated, very much as we did just 5 minutes ago, then the statement is that this relation is just a well-established fact. You could use just first principle of quantum field theory to show that in any gauge theory, it doesn't matter whether it's conformal or conformal, in the light-like limit, correlation function, asymptotic of the correlation function, will be given by exactly the same Wilson loop. There's only difference that this Wilson loop will be in the representation corresponding to field sitting inside the correlation function. In the exercise we did for unequal force theory, this was operator built out of the scalars which were enjoyed. And therefore this Wilson loop which appears in this relation will be Wilson loop in the joint representation. Then if you go to planar limit, the Wilson loop in the adjoint is just square of the Wilson loop is fundamental. And this square is exactly this square that appeared in all those formulas. So now at the level of QCD, this will be Wilson loop, let's say, for quarks in fundamental. Therefore, correlation function with electromagnetic currents built out of the quark fields will be directly related to the Wilson loop in fundamental representation. Now the question is about the relation of this, both this quantity to the amplitude. So what about these two links? So the first comment is that, as I already mentioned, if you just compare the corresponding expression and equal for QCD, you will find that due to contribution of additional diagrams, it will be much more complicated, if already at one loop level. Whereas Wilson loop is the same at one loop level. It's the same in QCD and equal for C. So there is no hope how amplitude will match Wilson loop for arbitrary kinematics. And then what happens? Let's now go to special limit. And the special limit I already mentioned previously. Let's now go to the limit when S much bigger than T. What's special about the limit? So I want to consider the same amplitude, foregoing amplitude. P1, P2, P3, P4. In the limit when actually S much bigger than minus T. So I want to go to a physical channel when these two particles are incoming, these two are going. So I want to consider the situation when momentum transferred in T channel is negative and S much bigger than minus T. So this is so-called radial limit. So what we expect to find this radial limit. In radial limit, you expect that this amplitude will grow with power. And the corresponding contribution is normally associated with the contribution of so-called Regge trajectories. So if you believe in the Regge theory, you will have to say that this quantity here should be given by the sum of the Regge trajectories. And each Regge trajectory will give you a contribution, which roughly speaking could be depicted like this. So this dashed line stands for the exchange of the Regge trajectory. Here you have P1, P2, P3, P4. So here you have certain effective vertices which are called residues on the Regge trajectories, and the contribution which come from this diagram from Regge series should be parameterized like this. So there is sum of Regge trajectories. Regge trajectory will induce you some behavior which grows as a power of energy, and here you have corresponding factor of Regge factor which depends only on t but don't depend on s. So these are what you're expecting from Regge theory. And so now let's compare this formula with what we have in unequal force theory. So you might ask this question: how unequal force theory matches this formula? So for this we have to do two things. First of all, we go to the planar limit, right? I told you that this expression is the level of all loops. It acts on the planar limit. So once you go to the planar limit, what you will find is that in this, in general, infinite sum of all Regge trajectories, only one trajectory will survive. And this Regge trajectory is so-called Glonn Regge trajectory. So the first implication is that this sum actually will reduce to a single term. And there will be some subleading corrections which are associated with so-called dotted trajectories. So this omega r of t will be definite quantity which is related to Glonn Regge trajectory. Now let's compare this function with this one. So here, if you look for this function in the form, let me write it like exponential omega r minus t logarithms s to minus t. Then this formula predicts you that you may have at the level of the logarithm's amplitude at most first power of the logarithms, right? But here you have explicitly at the level of the logarithms various terms which have second power of the logarithms. But now you notice it comes with negative sign. So if you sum this term together, you see that log square goes away. And therefore, in the difference of this term, you do recover linear behavior in S. Therefore, you can match this formula into this one, and then if you match it, what you will find this. So the first term, proportional Caspar normal dimension, comes from these two terms, and the last term, this one, comes from this term. Right? So from this you conclude that BDS on that indeed is in agreement with Regge behavior expected from Regge theory. And most importantly, if you just look carefully into this expression Z1, you will find that this formula actually is exact. Another way, in unequal force theory, there is no correction like this. So if you start from this formula, you go to Regge theory, what you will find, Regge limit, that Regge behavior on unequal force theory is exact. And exact in the sense that Regge behavior of this amplitude doesn't require the presence of leading corrections. So n equal 4, Superior-Mills, Regge exact. And actually, this observation has been later used by Claude Vittorio and Volodya Smirnov to push the calculation to remainder function to very extreme situation which correspond to so-called multi-Regge kinematics where lot amplification occur. So this statement has been verified at present up to 2 loops, not only for 4 but even 6 points, and we believe it should be exact in general for arbitrary amplitude, not necessarily MHV amplitude. So now let's go to QCD. So if you go to QCD, again, Regge theory will tell you that it should have exactly the same behavior. And indeed, there was a lot of attempts to compute the corresponding function omega r minus t in QCD. And what was done, it was first computed at 1 loop level, then at 2 loop level, and finally all loop expression had been formulated. Let me write you this all loop expression. So this formula I'm writing here is just the result of the analysis which has been performed in QCD. So two comments. The first comment, I told you QCD is not conformal series. Coupling constant is wrong. So the consequence in this formula, what you have two terms, both of them involve some function, and here I put A, which in QCD notation is called alpha S to P over MC, QCD coupling constant, which defined a very special scale, K square. So you have integral over this scale, which goes from minus T to mu square is the Fred cutoff, and here you have second term, which is so-called collinear anomalous dimension, also defined at the scale, which is minus T. So this expression, this relation here, is just a result of the computing of scattering amplitude, gluon scattering amplitude in QCD. Right? And this amplitude has Regge behavior, is definite prediction for the Regge trajectory.
Yes? Or
No, it's a result of the, it's statement, it's just a result of the analysis. Theorem, which is already 20 years old. So this statement is, this formula again, started the following. First it was computed explicitly at one loop, which was done by so-called BFKL, Balitsky, Fadin, Kuraev, Lipatov, back I believe to 78. At two-loop level, it was computed by Fadin and collaborator around 95, and all this all-loop expression was obtained in my paper 96. So again, just the result of the QCD analysis. But now let's try to ask the question whether the same QCD behavior of the amplitude could be matched against similar behavior of the Wilson loop. Right? We want to come back to this picture. So we know this in the Regge limit. What about these two quantities in the Regge limit? So you go to the Wilson loop in QCD, and you ask the question, what will happen to this particular Wilson loop if you go to Regge limit? So I told you that this Wilson loop knows about kinematics of the amplitude. So the momenta, here you have P1, P2, P3, P4. So now let's go to Regge limit. So Regge limit from point of view of momenta corresponded situation when S, which was P1 plus P2 square, much bigger than T, which is P2 plus P3 square. So what does it mean from point of view of this contour? It means basically that if you look for this contour and you look for these two diagonals, in this limit what will happen is that one of the diagonals, namely this one, will be much bigger than another diagonal. So this Wilson loop will be squashed. So if you go to Regge limit, what you will do, you will deal with object will be like this. So this will be x1, x2, x1, x2, x3, x4. So this will be S, this will be T, and here we're dealing sort of with Wilson loop, which is sort of squashed in this direction.
who is S? Sorry, S is x1 to x3. That's a bit confusing. Is it obvious that that configuration corresponds to S much bigger than T? Because S,
Again?
Is it obvious that S is much bigger than T? Because that diagonal is null, almost, no?
Which diagonal is null?
The one corresponding to S.
This one?
No, the other one.
This one?
Yes.
Why it's null?
It's almost null because it's...
Well, it depends. It depends from which point of view you're looking at this contour, right? So if you're looking from these are not like direction. So let's think about this one: P1, P2, P3, P4. So the Regge limit corresponds to situation when these 2 points are deeply in Euclidean, if you wish, from perspective. If there's like directions, so if these are all like directions. So we're going to the situation when these points x1 and x3. Actually, they're time-like separated in the Regge kinematics. And time-like separation much bigger, right? There's another space-time separation between another 2 points.
There is a third dimension missing.
Okay, depending on your imagination. But for me, once you familiar with this quantity here, right? So you have here only 2 scales. So this Wilson loop depends on 2 scales. One of the scales is one diagonal, another one diagonal. And there is also, since we're dealing with theory which doesn't have conformal symmetry, we have also scale mu square which will provide cutoff. So here we're dealing with a function which actually a function of 2-dimensionless quantities. So this one and this one. And then you ask the question, how this Wilson loop in QCD look like in this particular limit when the ratio of these two arguments is small, which correspond to radial limit. So the answer is the following. It has this behavior, which is just the ratio of this diagonal, and some power. In this power is some function of the coupling constant and smallest diagonal. And now if you compare this formula with this formula, you will find that after you replacing this one by S and this one by T, these two formula coincide. Which means that in the radial limit, what you have that overall amplitude goes to 4H Wilson loop in the radial limit, which automatically means, by the logic I formulated at the very beginning, that this amplitude recovers dual conformal symmetry in the radial limit. So which means that QCD has dual conformal symmetry in the radial limit only. Now if you compare this statement and that one, you immediately realize what's the main difference between QCD and equal force theory. In equal force theory, it's actually exact. You don't need to go to radial limit to recover this symmetry. In QCD, it's only in this limit you will recover some additional symmetry, which again tells you that there should be something integrability should appear in this limit. And indeed, it has been known already for some time that exactly in the radial limit, certain spin change will appear in describing of high energy behavior QCD scattering amplitude. So basically, I'm already running out of time. Just to summarize, so we started from unequal 4. We explored all possible dualities, and then we see there is a nice picture appearing with some amplitude related to the Wilson loop to the correlation function in very special kinematical situation. And then once you go to QCD, what happens that basically you're forced to go to radial limits to preserve those integrable structures. And the last comment, if you remember where QCD was formulated, the starting point for formulation QCD was so-called dual resonance models. So the first attempts for QCD appeared from the attempts to describe linear radial trajectories describing hadronic spectrum. So radial limit was always the driving force when people found a lot of interesting structures. And here somehow we're turning back after 50 years of development with the QCD in the radial limit, and we see some nice things appearing again. So since this understanding of duality of unequal 4 versus Wilson loops, historically it was found through the DSFT correspondence, then the main question appears, what would be the justification? What would be the analog of a DSFT correspondence which is responsible for this? Is there any string, whatever formulation, dual to QCD, which were responsible for this? This is the main question which I leave open just for discussion.
In BFKL, the beta function comes in at two loops and makes things more complicated.
Yes.
That doesn't seem to happen.
No. This is exactly. Sorry, I read the formula. If you remember formula, let me write it again. Since it's a nice formula, I wouldn't resist writing it again. Let's look for this formula carefully. So this formula for color energy trajectory, it has the following form. So you have integral 1/2 integral dk square over k square minus t mu square gamma cusp a over k square. I don't want to write the second time. I don't want to write it. So now imagine that when you're computing this coordinate in perturbative expansion, let me be scale. So what you do, you're expanding this object in powers of coupling constant, which is coupling constant defined in scale mu square. So how you do it? You start from cusp anomalous dimension, which is given by some expression QCD to loop level, and then what you do, you're writing coupling constant scale k square as a coupling constant mu square, and here you have beta function appearing explicitly. So now if you plug in this expansion inside, you will find that beta function will first appear at the level of two loops as a very special contribution, and this contribution will have a form. So omega r of minus t will, roughly speaking, modular factor 1/2 will be proportional to C1 A of mu square logarithms minus mu square over t. And then you have two-loop corrections. At the level of two-loop corrections, beta function will appear with a term proportional to the second power of mu square. And then there will be first power of logarithms which come from two-loop cusp anomalous dimension. So this formula, the formula I drew here, it's exact in the sense that it knows about beta function. And the only thing in which you want to compute this omega two-loop levels, even in QCD, you have to provide cusp anomalous dimension and beta function. If you go to n equal 4 theory, you just forget about running of the coupling constant. It just becomes function depending on the scale. And then it automatically reproduce to the formula which, again, it was written here.
So the trajectory is not even approximately linear, right? It is in the dual
you have to be careful because if you look, this formula, strictly speaking, it's valid in the region when t much bigger than mu squared. So if you look for integral from where this formula came from, the integral has this form. It was integral. There's only one loop. It was integral of some parameter k square, q minus k square, q square, alpha s, so omega, where q square is minus t. So what I did here, I just put here 2 minus epsilon, and I computed the interdimensional regularization. But if you just leave it like this, and formally if you put q square to 0, if you go to the origin of the radio trajectory, this q square goes to 0, so it vanishes, which means that this going trajectory will, for t equal to 0, it will go through its right value, which is 1. So spin of the gluon is 1, and therefore for t equal to 0, it will go through 1.
So this also answers my other question, because n equal to 4 supersymmetric, you don't have particles, so you cannot continue into the, like in Reggie theory, predict the spectrum like goes the integer change.
You have to be careful because we're mixing various things. First of all, the quantity which we're discussing here, what each of these quantities, so let's say amplitude, it's not physical quantity from point of view of Reggie theory. If you just remove regularization, if you put this parameter mu square to 0, the amplitude identically will vanish. If you want to discuss Reggie trajectories in physical terms, you have to go to the quantity which is, in fact, safe. Let's be scattering of two color singlet quantities, where it's exactly the setup of Beth-Kelp-Pomeroy. But then what will happen is that you have to go beyond planar limit. If you want to formulate the setup to approach problem with Beth-Kelp-Pomeroy, you have to go to the next level in the planar approximation. And again, so far we don't know how to extend this duality beyond planar limit. But what we do know is that if you go to Beth-Kelp-Pomeroy, which describes non-planar corrections with this amplitude, there you find integrability. So you do know that there's a level of Beth-Kelp-Pomeroy contribution to scattering amplitude, integrability is there. Which means that some integrability which is discovered here at the planar limit survives if you go to the planar corrections in the Reggie limit. So again, the Reggie limit is so special that if there is any symmetry in your problem, they will reveal themselves immediately once you go to the Reggie limit. Which means there should be, again, there should be a dual description. There should be dual description of the amplitude. I don't know whether in terms of the correlation function of the scattering amplitude, or Wilson, or whatever, you name it, which will make the symmetry explicit.
I have another question. Now, as I remember, Reggie theory goes far beyond the usual S-matrix theory, which is based on some very rigorous thing like unitarian crossing. But then Reggie theory goes on and it involves all kinds of assumptions about what happens in the complex angular momentum. Something happens, this happens, doesn't happen. And it's all inspired by some potential scattering that Reggie and so on. So a lot of people did not believe the details of it.
Okay.
So, but somehow this theory is smart enough to say all those things are true. All the assumptions are true.
You see that is the reason why we love this n equal 4 series so much, because in some sense you could say that n equal 4, if you're thinking about all possible gauge series, starting from QCD all the way to n equal 4. N equal 4 is special, it's maximally analytic. In other words, if you're expecting some nice analyticity properties appear, including those that you mentioned, they are there. But you find these properties only after you did the calculation. If you start from, if you just stare at the action, you would never even guess that such property, like the exactness of the answer, is there. Which again brings the same statement that there should be dual formulation of all everything I have said here, which make all the symmetry explicit.
Yeah, so I want to ask a question which I'm not sure makes any sense, but let me ask it anyway, which is that instead of, in a sense, going from G4 in deriving a connection to A4, can you start the other way around and start with A4 and somehow derive a connection to G4, but so that in a theory like QCD, you'd have not just a G4 contribution, but some sequence of terms that would fill in the suppressed terms in the Reggie limit.
Let me slightly formulate the question. You will see that where I'm driving you. Let's start from n equal 4 theory. Way much more simple in that sense. And then you can ask yourself the question. Let me start from the integrals, which were integral for A4, which at one loop level is scalar box, at two loop level is just double box. And then ask the question whether there is some kind of change of variables, whatever, another formulation which automatically will give you something which will look exactly as if you're calculating correlation function. In this case, we found the answer. The answer is you have to go exactly to this. If you're calculating G4 by the method so-called Lagrangian extensions, the one which I described here, you get exactly the same integral, one-to-one integral. If you go through the Wilson loop, it will be a completely different set of the integrals. At least when you draw the integrals, you will see that the level of two loops contribution to the Wilson loop, even like this one, it will move much more diagram, but if you sum them together, you miraculously reproduce A4 amplitude. So going from, what I ask you, if going from amplitude to the correlation function for QCD, we didn't try this. But there is an obstacle. Obstacle, again, has to do with the fact that once you go beyond one loop level, you have to deal with a contribution which will break conformality of your theory. And then if you're calculating correlation function, at the level of the correlation function, breaking conformality will appear at two loops. And breaking conformality of the amplitude appears at one loop.
I guess, I mean, more pedestrian, is there some sequence of additional correlation functions that can give you these terms that are suppressed in the...
Let me put it this way. I hope the answer is yes, but I cannot give you a constructive answer. I don't know. Let's put it this way. We didn't try this, but there are certain objections which you have to face if you believe that this is possible.
I mean, somehow you want to re-express the amplitude in some sense is some pattern all over over the gauge fields, let's say, and then you want to somehow, as I say, I don't think this really makes any sense per se, but you want to re-express the gauge fields in terms of some expansion. In some appropriate sequence of operators.
Again, given I have said, I believe that if you do in the radial limit, I believe in the radial limit again, it should be possible. In the radial limit, you
actually do this systematically.
Yes. If you start from the correlation function, you go from the very beginning in this limit, which will mimic your radial limit. Then, first of all, you'll find some simplification already of the correlation function, and after eventually the simplification will lead exactly to those integrals which appear for the amplitude.
I don't want to do it in exactly.
No, I understand.
Don't you think that you will do more or less in the other direction? You would start from the off-shell correlation function, decompose each field into one-shell modes.
That's the usual logical way to go, but I want to think about going the other direction precisely because somehow it seems as though there are missing terms in some expansion which are present in the amplitude and not present when you look at the correlation function.
Okay, related to David's question, if you're looking at the systematic corrections in QCD
Yes.
Reggie limit,
Yes.
can you say anything about the symmetry, let's say the next correction? Is there any...
You have to be careful. There is two types of correction. If you go to QCD, what I'm describing you here, this first line over there, it was planar limit of QCD amplitude. Right? You know, QCD amplitude. If you think it's planar, so you forget about non-planar corrections. As level of the already as level of planar corrections, you have to decide whether you're talking about leading Reggie trajectory, or you want to discuss subleading contribution as well. What's special about QCD compared to NQ4 that if you do calculation of this quantity in QCD, you will find kinematical variables which look like U over S. Here they don't appear. So once you have U over S in the radial limit, this becomes minus T over S minus 1.
That's not going to show up in the planar in the planar though.
QCD?
No.
Even the fact that you have quarks in the fundamental multi-joint?
Well, let's ignore quarks. Let's just
I just pull Young Mills.
It doesn't matter.
So then, again, if you're staying at the level of planar limits, then you basically have only global Reggie trajectory.
Right.
For global Reggie trajectory, this becomes the formula again. The formula I drew here. It involves two enormous dimensions. The Kasper enormous dimension and collinear enormous dimension. The statement is that this formula is universal. So once you found, for example, this Casper anomalous dimension and Klein anomalous dimension, let's say from 4 gluon amplitude, you could go further, for example, what Vittorio Claude did later. You could go to the process which involves many particles, and the Regge factorization will tell you that this multi-Regge kinematics, the whole process will factor out in various blocks, but you always will have gluon Regge trajectory in change in T-channel.
Well, what I'm talking about is the subleading corrections to the Regge limit.
I think that
In what?
break the
In what?
invariance. So it'll break the
No, but
invariance. So you're going to the limit S over T goes very large, but then it's of course subleading corrections.
those corrections, there's this one.
Yes.
Right.
This one.
That's the question that I was also asking.
No, this is a...
Can you reverse this procedure to come up with some correlation function?
I don't know. I don't know how to do it. And what I mentioned is Biscale Pomeroy is exactly about this term, not about that one.
So there's no echo of, I mean, you might think that there'd be an echo of dual conformal symmetry as you're walking down the series.
Well, there'd be some theory on it, and then the first order correction would give you the...
Yeah, somehow it gets, the dual conformal symmetry gets weaker and weaker as you march down, but in each order, at least the first, let's say the first order, you have some information.
Yes. I cannot give you a complete answer, but there is one special, for example, if you're thinking about where these corrections come from, simplest example, imagine you have QCD amplitude and you're changing in T-channel, not gluon, 2 gluons, by 2 quarks. If you the leading Regge trajectory comes from the exchange of the particle's maximal spin, let's say gluon. Once you go to exchange of 2 quarks, you will get correction in the same form. And therefore, your question would be that imagine I take QCD amplitude, I decompose in various pieces, and I concentrate on the piece which has 2 quarks exchange in T-channel. Whether this piece itself has some nice features. And there were some papers where people trying sort of to formulate this Biscale Pomeroy, the same picture, for gluon trajectory defined by 2 quarks. And there, to the best of my knowledge, people didn't find so far traces of integrability. So another way, coming to the question, I don't know whether it's...
I mean, the sort of picture, I think, really more that's close to what Steve is asking about and what I'm asking about is that, so you have some chain of gluons, right?
Yes.
But now suppose that all but one of them are in the limit, and there's one basically breaking of that limit that you then have to insert in all possible places. And you sum that up. So the question is, what's the correlation function picture from that contribution, which is precisely the first subleading correction, the first TORS correction?
I don't know. Understand.
Doing this crazy, nonsensical notion of re-expanding the fields in terms of operators so that you can then give some derivation.
So on the logarithmic scale, it's next order magnitude difficulty problem compared to leading trajectory. I mean, if Vittorio, you have some comment to make.
Well, I have a comment. Well, I actually have a question regarding the trajectory that comes out of the Wilson loop.
Yes.
I mean, as you said, besides the one loop trajectory of BFKF, there is the 2-loop trajectory by Fabin and collaborators identified.
Yes.
But the 2-loop trajectory is basically the beta function times the log square, as you wrote.
Yes.
Then there is the Casper anomalous dimension times the log.
Yes.
And then there are finite terms.
Yes.
Which the amplitude predicts precisely.
Yes.
Then you say, I have the all-loop trajectory, but the all-loop trajectory, I guess, you refer to the beta function term and the Casper anomalous dimension. Also the finite terms?
Yes. This was the statement. This was the statement of the paper. It appeared, historically what happened that after finding the performance calculation, the structures they obtained was exactly the one that dimensions. There was beta function term, which appears with double logarithms. Then there was this special number, which you know that for Casper anomalous dimension, there was this constant, which I didn't write right here. And at that moment, I did some calculation by various reasons. For exactly this light like Wilson loop, exactly this like Wilson loop. And once I saw the Fadian expression, I immediately realized that what Fadian, the expression for gluon trajectory is exactly what I obtained from this Wilson loop.
And 2 loops. But
2 loops.
Go beyond.
If you go beyond,
beyond 2 loop. Yeah. What do you know? I mean, you still know that the term proportional to the log is the Casper anomalous dimension.
If you go beyond 2 loop, you know that Wilson loop will definitely give you some expression for this constant we're discussing. You definitely know that if you go into the calculation of the amplitude, also will get similar contribution. The problem is you don't know neither one nor second one. So at this level we're staying right now, you have only two-loop expression for the amplitude, two-loop expression for the Wilson loop. So when I make the statement that this collinear trajectory is exact in the sense that it reproduces your result of the calculation, this formula has been checked to two-loop level. It matches exactly the result of the calculation. Beyond two-loop level, this question about the constant, if you wish, just conjecture that the Wilson loop will have to reproduce this constant.
Okay. As far as the beta function term.
Beta function term in Kaspanov's dimension is just theorem. It's prediction. It's prediction.
Tell any number of loops.
It is a prediction from Wilson loop will give you definite prediction for the structure of those Slobodin corrections. For example, imagine you go to three-loop calculation of the amplitude, which nobody had done so far. Yeah. So this gives you predictions. If you go to Blue-Raggi trajectory, you have to find sequence of term. The leading one will be one beta function, two beta function, Kaspanov's dimension, and the last term will be constant.
Yes.
And I'm claiming this constant will be exactly the one which comes from the Wilson calculation.
Maybe just one more.
Now, you discussed N equals 4 and then QCD. Now, what about N equals to supersymmetric theories?
Yes.
In particular, those that are one-loop finite.
Yes.
How much of these results do they expect to generalize to those cases without taking the Regge limit?
Basically, there are results for N equal to Sopyang-Mills theory, the calculation for the foreground amplitude.
I think it's not dual conformance.
And you basically at level of the one loop, right? At level of once you have beta function equal to series, they're finite, but you have one beta. No, finite. They're exact. There is one loop beta function. So once you have one loop beta function, by the same argument I gave here. So if you go computing this amplitude here, this beta function, you have to correct the argument of the coupling constant. This will appear through this topology of the diagram, which will break explicitly dual conformal invariance. So therefore, you're guaranteed that if beta function different from zero, I believe you could make more salient statements that dual conformal symmetry ought to be broken. But if you go to Regge limit, N equal 2 looks as good as QCD. All gauge theory will look like.
I have a comment on that. There have been some investigations of N equals 2 theories with regard to integrability, and as far as I know, the result was when it's an orbipole of N equals 4, it's more or less the same. But what you can do is, I think you can change the coupling constant. Although they are all finite, you might change their values. If they are all the same, it's an orbifold. If they are not all the same, then you also break integrability, although you get a finite theory.
But as you know, even in equal 2, if you think about the gradability, just take an equal to 0. You just look for the dilatation operator, it's breaking the gradability, but there is some subsector when the gradability is restored.
No, it's fully integrable.
If you just take n equal 2, just the plane n equal to 0.
Plane. I'm saying orbifold of n equals 4.
It's a very special restricted set of.
Well, if you look at the finite ones, it's I think you only need to put the coupling constants to a special ratios.
But let's just n equal to convention, n equal to Sopyang-Mills theory.
No, and then that's obvious that you break integrability.
True, but then you know that the gradability will, it's not that you break completely. It will be certain subsector when the gradability will restore it.
No, just that one loop, so what?
Two loops.
No, one no.
Two loops.
No.
It has been checked to two loops.
I don't think so.
Okay, the result of the calculation.
Your calculation?
Let's thank Gregory for this very beautiful talk.